So today we will learn about total internal reflection. So total internal reflection is a special type of reflection that occurs when a ray of light moves from a denser medium to a rarer medium. So suppose this is the boundary separating a denser medium from a rarer medium. Suppose this is the rarer medium and this is the denser medium. So a ray of light is initially in the denser medium and it is traveling in the denser medium and it is incident on the surface separating the denser medium from the rarer medium. So suppose this is the incident ray. At the point of incidence, we draw a normal. So as ray of light travels from denser to rarer medium, it obviously bends away from the normal. This is what we all know about refraction. The angle of incidence and the angle of refraction are related by the Snell's principle or Snell's law. Now suppose this angle of incidence in the denser medium, it goes on increasing. If it goes on increasing, at some particular value of this angle of incidence, this refracted ray will graze the boundary separating the two medium. If the angle of incidence I goes on increasing at some value of I, this refracted ray will bend more away from the normal. It will bend continuously, bend away from the normal. So when the angle of incidence, if it goes on increasing, it will reach a particular value at which the angle of refraction will become equal to 90 degree and the refracted ray will graze the boundary separating the two medium. So at some value of I, now this particular value of angle of incidence at which the angle of refraction will become equal to 90 degree, that angle of incidence will be called as the critical angle of this pair of denser and rarer medium. So if the angle of incidence goes on increasing at some value of I, that is equal to IC, this IC is called as the critical angle. Is the critical angle. So at some value of the angle of incidence, the angle of refraction will become equal to 90 degree and the refracted ray will graze the boundary separating the two medium. Okay. And if the angle of incidence is increased further beyond this critical angle, then there will be no refracted ray at all. This refracted ray will bend so much that actually it will reflect back into the denser medium, and then the phenomenon will be called as total internal reflection. So when the incident ray is greater than the critical angle, the refracted ray will bend back into the denser medium, and in its true sense it is no more the refracted ray, it is actually the reflected ray. So reflection occurs, and that type of reflection will be called as total internal reflection, and it will obey all the laws of reflection. So I have shown three diagrams through which we can compare ordinary refraction, the refraction that occurs when the angle of incidence is equal to the critical angle, and total internal reflection when the angle of incidence is greater than the critical angle. So in the first diagram, this is ordinary refraction. The ray of light is moving from the denser to the rarer medium and it has bent away from the normal. So this is the situation when the angle of incidence is less than the critical angle. So in that case, ordinary refraction will occur. When the angle of incidence is equal to the critical angle, then the angle of refraction is 90 degree and the refracted ray grazes the boundary separating the two medium. The third situation is the angle of incidence is greater than the critical angle. And when angle of incidence is greater than the critical angle, there is no refracted ray. The ray has actually reflected back into the same denser medium and it obeys the laws of reflection, and this situation is called as total internal reflection. So instead of refracted ray or instead of refraction, we get the principle of reflection. So this is called as total internal reflection. Unlike reflection at the surface of a mirror, this reflection is special in that sense. Here there is no loss in energy, because whenever reflection at the surface of a mirror occurs, some amount of light is absorbed by the surface. But in case of total internal reflection, it is more advantageous because you can say that 100% energy is reflected back. So in the case of total internal reflection, 100% light energy is reflected back, and so it is very much useful in case of periscopes, binoculars, certain type of prisms. It has a great practical application in different cameras, etc. So this type of reflection you can call it as 100% reflection. So 100% energy is reflected back. No absorption of light occurs at the surface, separating the denser medium and the rarer medium. So the two conditions that are necessary for total internal reflection, so you can say conditions for total internal reflection. The first condition is the ray of light must travel from denser to rarer medium. You will never get total internal reflection when light is moving from rarer to denser medium. So the first condition is that light must travel from denser to rarer medium. And second, the angle of incidence must be greater than the critical angle. Second is angle of incidence should be greater than the critical angle. Now this critical angle is always defined for a pair of medium. The critical angle for water air is different from the critical angle for glass versus air. So depending on a pair of medium, the critical angle will differ. So angle of incidence is greater than the critical angle for that particular pair of medium, at which total internal reflection occurs. So these are the two conditions for total internal reflection. So now let us take the examples of some prisms at the surface of which total internal reflection occurs. So this type of prisms are called as total reflecting prisms. So we take the example of some prisms called as total reflecting prisms. The first one is, suppose it is a right angle isosceles prism. that is a right angled isosceles prism. This angle is 45 degree. This angle is also 45 degree. And this angle is 90 degree. So suppose a ray of light falls perpendicularly on one face. Suppose the prism is A, B, C. So on the face AC, a ray of light is incident perpendicularly. So this ray of light that is incident perpendicularly will follow its path. And now this ray of light, after following its path, suppose it is incident at the point P of the face AC. So at the point P, if we draw a normal, we can find the angle of incidence. What will be this angle of incidence? So this is 45, this is 90, this is again 45. So this angle is also 45 degree. Suppose it is given that the critical angle for air versus glass is 42 degree. Let critical angle be equal to 42 degree. Suppose the critical angle between glass and air is 42 degree. Now you see that when this ray of light has propagated up to the point P, the angle of incidence is greater than the critical angle. So if angle of incidence is greater than the critical angle, total internal reflection will occur. Remember that the light is moving from denser to rarer medium. Initially, this is the rarer medium that is here. So rarer to denser, then denser to rarer. So when it is inside the prism, it is definitely moving from denser to rarer. So now the critical angle for glass versus air is 42 degree. This angle of incidence is greater than 42 degree. So total internal reflection will occur. This ray will not move in this manner, neither it will graze the boundary. It will reflect. It will reflect, that means the angle of incidence will be equal to the angle of reflection. So this angle of reflection is 45 degree, that means the ray will move in this manner. The ray will move in this manner. So now this angle is also 45 degree, that means the ray has rotated by 90 degree. So when it hits this surface DC, this angle is also 90 degree, if you see. This is 45, so this angle is also 45. So this becomes a right angle triangle 45, 45, 90. So now the ray will again follow its path. It will not bend further. Because we know that if the angle of incidence is 0 degree, that means if the ray is perpendicular to a given surface, it does not deviate. So the ray follows in this way. So you can say that the ray has been rotated by an angle of 90 degree, and this type of prism is used in periscopes. It is used in periscopes. In place of a plane mirror, we definitely use this type of total reflecting prism in a periscope, so that the intensity of the image is more and we can get a more prominent image. So you see that light suffers total internal reflection when it is moving from denser to rarer medium in this type of prism, and hence it is also called as a total reflecting prism. Now if you take the same prism and you can see that the ray will deviate by 180 degree. In this case the ray has deviated by 90 degree. This ray has deviated by 90 degree. The ray has deviated by 90 degree. You can show an example where the ray can be deviated by 180 degree also. So let us take that example. The same prism I will use. So suppose the prism is this right angle isosceles prism is kept in this manner. This is 90 degree. This is 45 degree. And this is 45 degree. Suppose the prism is named as A, B, C. Suppose a ray of light is perpendicular to the surface BC. This is a ray of light which is perpendicular to the surface BC. Because the ray of light is perpendicular, it will not deviate, it will follow its path. And suppose this ray, after following its path, is incident at some point on the surface A. At that point we can draw a normal. So now you see, remember that the critical angle I have set as 42 degree. So if the angle of incidence is greater than 42 degree, when the ray is moving from denser to rarer, it will obviously show total internal reflection. So now this is your angle of incidence. So this is 45, this is 90, this angle is 45, so this angle is also 45. Which means that the angle of incidence as the ray is moving from denser to rarer, because this is made up of glass, so the ray is moving from denser to rarer, and now your angle of incidence is greater than 42 degree, so total internal reflection will occur and it will move in this manner, because this will make the same angle 45 degree. The reflected ray will make the same angle 45 degree. So it will rotate by 90 degree and it will hit the surface AC at some other point. On that point, at that point on the surface AC, we draw a perpendicular. Now, what will be this angle? This angle is 45, so this angle is 45. This is 90 degrees, so this angle is 45. That means because this is perpendicular or this is the normal, so this angle is also 45 degrees. Now again, the ray is moving from denser to rarer, glass to air, denser to rarer. An angle of incidence is greater than the critical angle. So it will again total internally reflect. And now this angle will be 90 degrees, so it will follow its path and move in this manner. So you see that the ray has now deviated by 180 degrees. 90 here and 90 here. So the ray has deviated by an angle of 180 degrees. So deviated by deviates by 180 degrees. And this type of prism is used in some cameras and binoculars. This type of prism is used in some cameras and binoculars. And those binoculars are called as prism binoculars. Used in cameras and prism binoculars. So actually, you can also get an image which is rotated by some specific angle in this case. So suppose, let me draw another pair of ray, then you will understand it. Suppose this is the object, suppose this is an extended object. One ray I have shown, let me show another ray. Suppose another ray which falls perpendicularly. This ray which falls perpendicularly will follow a similar path. It will deviate by 90 degree here. It will move on, and here also it will deviate by 90 degree and follow its path. So now you will get the image of this particular object in this manner. Because the ray has deviated by 180 degree, the image of the object AB will be some A dash B dash. So it has tilted, you can say. So this is another application of triangular prism, a right angled isosceles prism. We can take many such examples. So let me take another example of that right angled isosceles prism. The critical angle between glass and air remains same, that is 42 degree. So now suppose a ray of light is moving parallel to the base of the prism. Suppose this ray of light is moving parallel to the base BC of the prism and it strikes at some point on the surface A. So the light is moving from rarer to denser medium. It will bend towards the normal and it will be incident on the surface BC at some point in such a manner that it will undergo total internal reflection and then it will move parallel to the base of the prism. Now these angles that it makes, we have to apply trigonometry in order to calculate that, which might be difficult. So that's why I am not calculating, but still just remember that these angles at the point of incidence on either surface, definitely after conducting experiments, what we have realized is that in the case of a right angled isosceles prism, if a ray is parallel to the base of the prism BC, then it will deviate, it will refract at this point, and then when it hits the surface BC at some point, it will do so in such a manner that it will undergo total internal reflection, because at this point the angle of incidence becomes greater than the critical angle, and so total internal reflection occurs, and after hitting the surface AC, ordinary refraction occurs and it moves out of the prism, but this emergent ray remains parallel to the base of the prism. So suppose this point is P and this point is Q, and let me call the incident ray IP and the emergent ray as QE. Then this IP remains parallel to QE. Also, IP is parallel to the base of the prism, and this emergent ray QE is also parallel to the base of the prism. Experimentally, this we have realized. So now let me take another pair of ray, another set of ray to demonstrate how it will invert the image of an object. So suppose, let me take another ray which is parallel to the base of the prism. It will move in this manner. It will undergo total internal reflection and it will emerge in this manner. So this is another set of ray. So now suppose this is your object MN, then you will get the erect image here, which will be M dash N dash. So because this type of prism can be used to erect the image of an object, it is also called as erecting prism. This type of application is called as an erecting prism. And this type of prism is used in projectors. It is used in slide projector. So the erecting prism is used in slide projector. So as a result of refraction, after emergence, the rays are inverted, and so this type of application is also called as an erecting prism. So let us take more such examples. Let us consider now an equilateral prism. Suppose the critical angle between glass and air remains same, that is 42 degree. So let me consider an equilateral prism now. So suppose this is an equilateral prism. Obviously, the angles are 60 degree each. This angle is also 60 degree. Let me consider a ray perpendicular to the surface AB, and suppose it moves in this direction. This ray is perpendicular to the surface AB. Because it is perpendicular, it will follow its path, it will not deviate, and it will hit the surface AC at some point. At that point of incidence on the surface AC, we draw a perpendicular. Now, what will be this angle of incidence? This is 60, this is 90. 90 plus 60 is 150, so this angle is 30 degree. 90 minus 30, that is 60 degree. So this angle will be 60 degree. This angle of incidence on the surface AC is 60 degree. Now obviously 60 degree is greater than the critical angle 42 degree. So the ray will suffer total internal reflection. The reflected ray will make the same angle 60 and it will move in this manner. Now suppose it moves in this manner. Is it possible? We have to realize this. Suppose the ray is moving in this manner. Whether it is possible or not. If you consider this triangle, this is 60, this angle is 30 degree. So this angle has to be 90 degree. That means the ray, after reflection, after undergoing total internal reflection, this ray will definitely be perpendicular on the surface BC. There is no other option left. This ray has to be perpendicular on this surface BC. Because again, if you calculate, this is 60 degree, this angle is 60, so this angle is 30 degree. So obviously this angle has to be 90 degree. That means the ray will now follow its path, because a ray, if it is incident perpendicularly, it will not deviate and it will follow its path. So this type of refraction will occur. So now you can say that in this situation, that this was the incident ray. The incident ray was moving in this direction. So what is the deviation of the ray? So this is the total deviation of the ray. And this angle is obviously 60 degree. Because this remains a straight line. 60 plus 60 is 120. 120 plus 30 is 150. So this angle is 30 degree. This angle is 30 degree. So the total deviation up to this point, total deviation is 60 degree. So the ray deviates by 60 degree. So the incident ray here, it deviates by 60 degree. So we can consider more such examples. Suppose we take a prism, a right angle prism, but not right angle isosceles prism. The other angles are suppose 30 degree and 60 degree each. And let me say that the same critical angle, that is 42 degree between air and glass. So let me consider this type of prism. This is not a right angle isosceles prism. Suppose this angle is 30 degree, this angle is 60 degree. Suppose it is a prism ABC. So suppose that we consider a ray that is perpendicular to the surface BC. Incident ray is perpendicular to the surface BC of the prism ABC. So obviously the ray being perpendicular will follow its path, it will not deviate, it will move in this direction, and it will be incident at some point on the surface AC. So at that point of incidence we can draw a perpendicular. So now the ray is moving from denser to rarer. What will be this angle? Depending on this angle of incidence. So this is 60, this is 90, 150, this is 30. So this angle has to be 60 degree. So now you see that the angle of incidence at this point is 60 degree. So it will undergo total internal reflection and it will move in this manner. This is the reflected ray that will make the same angle 60 degree. Now at this point of incidence on the surface AB, we will draw another perpendicular or normal and we have to find this angle. So if you see, This angle is 60 degree. This angle is 30 degree. This is actually a triangle, definitely. So, what will be this angle? This angle is 90 degree, we know that, because it is a perpendicular. So, this is 30, because this is perpendicular. So, 30 plus 30 is 60. This angle is obviously 120. This angle becomes 90 degree. So, 120 minus 90, this is 30 degree. Now you see that angle of incidence at this point is less than the critical angle, and the ray is moving from denser to rarer, so it will bend away from the normal. So this will bend away from the normal in this manner. So this is the final path of the ray. So the ray will bend in this manner. Because the angle of incidence is less than the critical angle, it will undergo normal refraction. As it is moving from denser to rarer, it will bend away from the normal and follow this type of path. We can take more examples.